Chalo. Yeah, Bopeto, tell me your doubts.
Yeah, so atomic spectra.
Spectra. Okay, let's start. To understand atomic spectra, we don't need to know much. Rutherford model is enough. Okay, so basically, nucleus, one cell, next cell. There can be many more. Okay, 1, 2, 3, 4, 5. Okay.
Yeah.
Now, suppose let's consider a simpler case. An electron is at a little bit higher energy, so it is in the second cell. Okay, it may lose that energy and fall back to the first cell. Okay, fine na?
Yeah.
So the energy that it lost will be emitted out as a photon. Yes or no? So we will get a photon. Yes. Now, when this light is emitted, that light will also have a wavelength lambda. Yes or no? Now, to obtain that wavelength, we have a formula. The scientists, they did many experiments on this, and they got one empirical formula. It's like they observed all the results, like how much wavelength is obtained every time when the electron is transitioning, right? And they gave us a formula. So, can you tell me, can you write down the formula? No, na? That formula for finding out wavelength is, wavelength equals what? R into 1 by, sorry, not wavelength. It will be 1 reciprocal of the wavelength, right? 1 by n1 square minus 1 by n2 square. Fine. So this is the wavelength of the light which was emitted. This R is a constant called Rydberg's constant. Okay, this n1 is the first cell, is the energy, n1 is the lower energy cell. Okay, the number of the lower energy cell. That means always remember n1 will be less than n2. Okay, fine. So wait.
So, sir,
Hmm.
if it's going from 1 to 2, shell number 1 to 2.
Okay, now see, electron will never go from cell number 1 to 2. It will never go from a lower energy cell to a higher energy cell. Okay.
When it is extra energy.
Yeah, then it can go. Yeah, that's right. Then we can just use the same formula.
Yeah, no, like N1, then in this case, cell number 1 will be N1.
Still, the smaller one is still going to be the n1.
Yeah, and then if it comes down from cell number 2 to 1,
Then also n1 is 1, n2 is 2. Always remember, in that formula, n1 has to be lesser than n2. Okay? Because otherwise the wavelength comes out negative, na? Yes or no? Okay. Now, so we had some things called Lyman, Balmer and all, na? Lyman series, remember? Lyman series. So what is Lyman series? Lyman series is nothing. It's only the set of wavelengths. The set of wavelengths where we have n1 ka value fixed at 1. Okay? Is fixed as 1. That means all the wavelengths which we are obtaining when the electron jumps from second to 1, third to 1, fourth to 1, those will all come under Lyman series. Okay? Understood? So for example, okay, before that, now similar to Lyman, there is what? There are some more series, na? Lyman, Balmer, Paschen, Brackett, Fund and all, right? Okay, now let's get to this. The shortest wavelength. for Lyman. How do we get the shortest wavelength for Lyman series? Shortest wavelength means, remember, if the wavelength has to be short, obviously the frequency has to be largest, right? Highest frequency, yes or no? That means the emitted photon, the photon which was emitted will have highest energy. And highest energy means, on what factor does the energy of the photon depends? It depends on the difference in the energy levels, right? The energy of the emitted photon depends on the difference in the energy levels in the two cells, right? So maximum, as we go to larger cells, the energy increases, right? So which cell will have the maximum possible energy? The cell which is at infinity, right? Yes or no? So as we go further away, the energy increases, so the infinite number of cell will have the largest energy, and the lowest energy possible is going to be n equal to 1, right? So for maximum energy, we need the transition to occur from infinity till 1, right? So in this case, put n1 equal to 1 and n2 equal to infinity. That's how we solve the problem of shortest wavelength. Okay? Okay, is that fine? Okay, fine. Now the most important thing is got it? Yeah, done. Chalo, bye. Welcome.